Radiation heat transfer, part 1. Students, as we all know that heat transfer can take place in 3 modes: conduction, convection and radiation. In case of radiation, heat transfer takes place in the form of electromagnetic radiation, for which does not require any material medium. That is, it can take place in vacuum. This is the only heat transfer which can take place without any medium. And it is very important to study the radiation, that is the means of basic life on the earth, as all the energy on the earth which we are getting from the sun are in the form of radiation. Before understanding radiation, we should understand the electromagnetic radiation spectrum. It can clearly be seen that the entire electromagnetic waves, that is in which frequency ranging from 10 raised to power 4 to 10 raised to power 20 hertz, and wavelength is ranging from 10 raised to power 3 meter to 10 raised to power minus 12 meter, is called as radiation spectrum. We are most interested in the thermal radiation, for which spectrum, electromagnetic radiation spectrum, ranging from 0.1 micrometer to 100 micrometer. It includes some ultraviolet radiations, all visible radiation which is called as light, and infrared radiation. Now radiation heat transfer always takes place whenever a body is above 0 Kelvin temperature, then it will emit, absorb or transmit radiation. More we will heat it, more will be the radiated energy. Okay. For understanding all the 3 modes of heat transfer, we can take the example of kettle on the stove. Kettle heats the water by conduction. Water circulating in the kettle transfer heat by convection, and near the stove air would feel warm due to heat transfer by radiation. Now again, I will give emphasis on the fact that radiation needs no carrier or medium required, or even if medium is there, then the phenomena of radiation gets diminished. For this, I am considering 2 cases. First case in which medium is participating. Because of that, a part of the radiation gets absorbed and becomes smaller Q. And in case of medium is not non-participating, means the radiation takes place in vacuum. In that case, the total heat transfer by this radiation is capital Q. Clearly, small q is less than capital Q. Now, fundamental concepts of radiation is that the radiation is emitted in different wavelength and different directions. If we are considering the spectral distribution, then that will depend on the spectra of the light, that is wavelength and frequency. But in case of directional distribution, it depends on the direction of light. Every substance which is radiating have 3 fundamental properties: reflectivity, absorptivity and transmittivity. Reflectivity is the ratio of reflected radiation to incident radiation. Similarly, absorptivity is the fraction of incident energy that is absorbed, and transmissivity is the fraction of incident energy that is transmitted through the object. These all 3 radiative properties, reflectivity, transmittivity and absorptivity, are depends on wavelength and temperature, and their values lies between 0 to 1. By using the principle of conservation of energy, we can easily establish that the sum of all these 3 for any substance is always equal to unity. In this course, we will deal with only opaque surfaces in which transmission becomes 0, so alpha plus rho equal to 1. Now, Blackbody addition. For studying the radiation heat transfer, first of all, we have to take some assumptions. The basic assumption is that we are considering that the body which is radiating heat is a black body. What is black body? Black body is an ideal emitter, means energy emitted by any real surface is less than what is emitted by a black body. Following are the assumptions involved. It is an ideal emitter. At every frequency, it emits as much energy as or more energy than any other body at the same temperature. If it is a diffuse emitter, the energy is radiated isotropically independent of the direction. Now we will define one more important parameter for the radiation heat transfer, and that is called as monochromatic emissive power E lambda. It is defined as the rate of heat transfer per unit area at which the surface emits thermal radiation at a particular wavelength lambda. A black body has the highest E lambda for any given wavelength. Now there is a criteria for a perfect black body given by the Planck. A black body allows radiation to enter but not reflect. Then black body possesses the minimum thickness adequate to absorb the incident radiation and prevent its re-emission. And black body satisfies severe limitation upon scattering to prevent radiation from entering and bouncing back out. So these are basic assumptions, and we can easily see that the assumption of black body is a hypothetical one. This cannot happen in the actual life. Now there is an important law called the Planck Distribution Law, according to which theoretical spectral distribution for the emissive power of black body is a function of lambda and T, and it can be written as following, where CV and C1 and C2 are constants. The Planck distribution is shown in the following figure as a function of wavelength for different body temperature. Basically, this diagram is this one. At different temperature, emissive power is plotted with wavelength. We can have following conclusions from this figure, that at a given wavelength, the emissive power increases with increasing temperature. As the temperature increases, more emissive energy appears at shorter wavelength, means the graph is shifting towards the left. For low temperature, all radiant energy falls in the infrared region and is not visible to the human eyes. That is why only very high temperature objects such as molten iron can glow. Okay, we should know that sun can be approximated as a black body at 5800 Kelvin. Now, as we have already discussed that till now we have discussed about the black body, which is a perfect emitter. Now, for considering the real emitters, we will introduce a new term called emissivity. The ratio of emissive power of body to the emissive power of black body at the same temperature is called as the hemispherical emissivity surface. It is defined as the E upon EB, where emissivity depends on the temperature, wavelength and surface smoothness. Clearly, its value is equal to unity for the black body. In most solids and liquids, the radiation emitted from interior are absorbed by the adjacent molecules, thus making it a surface phenomenon. But in case of gases and semi-transparent solids, radiation is a volumetric phenomenon. Now, for considering the emissive power in the radiation, there is a law, very important law called Stefan Boltzmann Law. According to this, the total energy radiated per unit surface area of a black body across all wavelengths per unit time, also known as the black body radiant excitance or emissive power, is directly proportional to the fourth power of the black body's thermodynamic temperature T. EB is proportional to T raised to power 4. When we replace the proportional to sign by equal, then there is a constant called sigma, Stefan Boltzmann constant. Its value is 5.67 at 10 to the power minus 8 in SI unit, where T is the absolute temperature in Kelvin. Okay, as we all know, for a real body, emissivity is equal to E upon EB. That's why we can easily calculate E for the real body by using this epsilon is equal to E real body is equal to E sigma T raised to power 4. Now there is Wien displacement law as discussed in the Planck distribution law, that if we plot the graph between spectral energy density and wavelength, then this will be like as given in the figure. As the temperature increases, the value of wavelength at which maximum emissive power takes place is shifted towards the left. And as per Wien's displacement law, the black body radiation curve for different temperature peaks at a wavelength inversely proportional to the temperature. When we remove the proportionality constant, then it becomes lambda maximum into T is equal to constant. This expression can easily be derived by differentiating or by using the calculus for the equation given by the Planck's distribution law, where T is the absolute temperature in Kelvin and the value of C is 2.898 × 10⁻³ as given by the Rayleigh engines.